All right, welcome everyone to our session on Ray data. Ray data builds upon Ray compute. So I'll just take a couple of minutes to cover what we did the last time. I mentioned some foundational ideas of distributed computing, namely, when you have a lot of resources and they are heterogeneous, compute resources, you have data scattered all over the place. They are quite complicated issues when you try to do a distributed compute. For example, you would like to keep data as close local as possible. So in other words, if there's a hard disk or there's some storage that is local, you want to make sure that the local compute goes and computes on that data. You don't want to take that data, transport it over the network to a far off compute node. That's not as efficient, isn't it? So those are some of the aspects that you do. We also realize that we live in the world of distributed compute because that's how you get fairly good economics. You can use so-called commodity hardware to do a lot of computes. That was the main selling point of some of the early distributed compute frameworks like the big data framework. It was very, very successful using commodity servers, commodity hardware. You could work on petabytes of data and do a lot of computes very, very efficiently. You could get most of the parallelization that you wanted. You could do it at a fraction of the cost of doing a vertical scaling up in mainframes. And it became a de facto standard. Today, we hardly even speak of big data, even though the concepts are still there. They have been subsumed into the cloud frameworks. All of those ideas are now more or less taken for granted, and we tend to forget what a deep technology stack it is. So distributed compute, you have to worry about latencies, heterogeneous environment, failures, lots of failures. Again, a quick recap of what we did last time. And we talked about something that used to be important consideration, the CAP theorem. You can, in a distributed environment, either because of actual partitioning, because a network gets partitioned, which is much more rare, but because of transient and intermittent latencies that almost always plague distributed systems. So you have a trade-off. You have to choose, because in a distributed system, you have to have partition tolerance. Therefore, you have to make a choice between prioritizing consistency or prioritizing availability. Now, there are different kinds of systems. For example, Cassandra is an eventually consistent system. HBase, Bigtable of Google, and HBase in the open source Apache. They are highly consistent systems. In practice, what happens is that the gap is narrowing as these technologies mature. We are talking about milliseconds for eventual consistency, and availability in these systems remains extremely high as hardware gets better, as technology gets better. So nevertheless, from a theoretical perspective, these three things we have to remember that in complex distributed systems, oftentimes you can't have everything. You have to make some trade-offs, prioritize something over the other. So with all of that, we mentioned that distributed computing is hard. In fact, those of you who go through graduate school, undergraduate, upper division courses would remember that after doing the operating system course, then you go and do the distributed systems course. And distributed system course nevertheless still feels hard. Right? Because distributed computing is not an easy topic. There are many nuances, especially the programming part of it. There are many nuances in building it up when you try to build something up. Therefore, they have flourished many very successful distributed computing frameworks that do the heavy lifting for you and make it so simple that to you, it looks as though you're doing some local compute on your desktop. In reality, it is as close to local compute as they can make it. But in reality, what you're doing is you are there, you're sending the workload over to a distributed compute environment. The distributed compute environment magically does a lot of the work, but to you, it appears almost as though you're doing local computes. There's, like, for example, in the case of Ray framework, right? You just have to insert the word remote compared to a very basic uh, uh, Python client. Like, for example, we said, suppose you have a class called X and you want to imagine that there's a class which is a counter and you want to instantiate it. You can say X instance is X and then X instance increment. That would be a local, that's your standard vanilla Python code, which would run locally. But to make it run on a distributed platform in Ray, all you have to do is you just before the constructor, you add the word dot remote, or before any function invocation, you increase it. So here you say increment function, and this is the constructor function, but in both of them, you sort of interject the keyword dot remote. And when you do that, it is as simple as that. It becomes a remote compute upon a distributed compute and cluster. And you really don't have to worry about the intricacies of where the job is run, how the workers are managed, how the data is moved, and none of those you have to worry about. So that's something we talked about the last time. We said that the Ray framework has emerged in machine learning because we are talking about MLOps, has emerged as one of the de facto leading frameworks for compute, right? And inference and training and so forth. So it is capable of data parallelization. It's capable of compute sharding and data sharding. Lots of things. These are hard topics, and we talked about it. It can do that, right? And at the end of it, we end up with 3 or 4 basic constructs at the core, Ray core level. What are those basic constructs that we talked about? That a function, to make a function into a distributed compute, it becomes a task. You just have to annotate it with @ray.remote. It becomes a task. It's a stateless thing. If you want it to have internal states, you would rather start with a class with the same annotation @ray.remote. It becomes into an actor. And whenever you invoke tasks or methods in the task or in the actor, what it returns are not the answers, because that would block you, but it returns something called a future. A future is a placeholder. It basically says, here's a box. When I'm done with the work, I'll fill the box with the answer, right? That's one way of looking at it for future. So you can, what it does is it frees you on the client side to go ahead and do other things with the assumption or with the promise that that box will eventually get filled, right? And that helps you on the client side parallelize or push a lot of tasks, pipeline a lot of tasks onto the distributed cluster, right? And then once you have pushed a lot of tasks, then sort of pull a wait around for the ones that really matter to you at that time to get that. So those are the 3 important things. And the 4th thing is that they also maintain, Ray framework also gives you a distributed memory object store, right? It takes the memory of all of these machines and creates a distributed memory object store into which all of these workers, all the nodes, the internals of Ray will use it as though it is the global memory, right? Which it is. It acts sort of like a global memory, right? Now, we did a couple of examples, and we will, I hope you did do those homeworks. But now, with that recap, I would like to move to the topic of Ray data. So, and let me pull through the writing board, and we'll get into the writing mode. Ray data. And you can almost call it that.
As if you're not sharing.
Oh, I am not sharing the screen. Oh, I apologize. I tend to forget this repeatedly. Am I sharing it now?
Yeah. We can see it now.
Yeah. Okay, Ray data. So what is Ray data? A very naive or simple way to start with it is Ray data is in some sense a data, what in PyTorch you would call a data loader. or in many frameworks, you call a data loader. What does it mean? Suppose data is sitting there in CSV file, in JSON, in database, in whatever, XML, over a URL or whatever a format. In many one of those sources, it is sitting there. And or in S3, Cloud S3 or Object Store, Google Object Store, etc. And you want to load the data, especially if the dataset size is humongous, right? So, and by the way, let me also add some distributed file systems while we are at it. So any kind of a distributed file system that may be there. What data loaders do is that they load the data from the source that you point to and create an in-memory representation of it in some sense, in memory. Now, that may look like, okay, now what's the big deal about it? Pandas is the same thing. For example, if you remember, if you did something like import pandas as PD dot read, let's say whatever, read, for example, CSV, it would read that into a data frame, isn't it? So in a way, pandas is also a data loader. The difference between that and Ray is a distributed compute aware data loader. What does that mean? It means that suppose your data actually is distributed across many disks and many nodes in the cluster. Let's say that your data is here. You have one node here, one node here, one node here. Yeah. What it will do is it will create the appearance, or it will load the data. Ideally, as it loads the data into memory, it will keep it local. It tries to preserve locality of data. And to a large extent, it tries to keep the computes local too. It ships out whatever computes you do, it ships it out. Now, those of you who are familiar with Spark or with MapReduce, we are talking of exactly the same thing. If you remember, when you call on a Spark or data set, you call map, like, all of these things like map, flat map, filter, group by, aggregate, all of those operations that you call, those operations, the machine internally will try, that the framework internally will try as much as possible to optimize and keep computes local. Are we making sense? Like, for example, suppose you had a bunch of numbers. Let's say one data set is DS1 is a set of numbers. Lots of numbers. Let's say they are revenue numbers, whatever it is. There are some sales numbers. But these numbers in reality are coming from multiple of these nodes. So you realize that this data set is actually creating the appearance of one array, but in reality, it is made up of local data representations. So when you do DS1, you map it, let's say each number x to its square of that number, right? I'm deliberately writing sloppy notation to make it obvious what we're doing. What does a map function do? A map will take every item. For map comes, by the way, from functional programming. For every item, generate a new item based on some function or rule. Right? Here, the function is the square function. You're squaring x. Right? So what will it do? It will create data set 2. But you realize that this function can be pretty much done locally. There is no reason to move the data away from the nodes. You can go and the data set that is here, this little partition, out of that, you can manufacture the square part of it, x squared, to create a local data here. Likewise, the data that is here at this node, this also, you can do a local compute to generate the X square here, isn't it? So you could create this data set too, which again appears as though it's global, and it is global, but internally has been optimized, and to a large extent, the computes have been kept local. This should be very reminiscent for those of you who are used to a functional programming paradigm. For example, the Spark. Those of you who are used to Spark, obviously this looks very, very familiar, hopefully to you. And it is deliberate. Actually, the creators of any scale of this at any scale of array framework, some of the founding creators are the same who created the Spark framework, the Apache Spark framework. And so there is a lot of commonality of thinking. Another way of saying it is that once you find a successful way to do something, why not pursue it into the future? Just with more modern or with more machine learning specific optimizations baked in. And that is something that you see with the dataset framework. What it does is you get a lot of optimizations or thinking that is machine learning specific. Right? So what are those machine learning specific optimizations that you may mean? Imagine that there is a data, large silo of data, right? And this data may be distributed across multiple machines, multiple nodes. Now, suppose I have GPUs, GPU 1, GPU 2, GPU N. You have N GPUs. Now, you realize that when you have N GPUs, where is the data loaded? If you look, if you so-called call a data loader, it will load it to local. It will load it to local representations. Wherever this GPU is, there would be necessarily in that machine a CPU and a core, and a CPU and a memory. There would be a CPU and there would be a memory. Does that make sense, guys? Right? There would be some local memory. So this brings us to data sharding, and as you push it to the compute, what this framework does very, very well is that when you try to do some compute on the GPU, it will, in a very efficient manner, try to push local data. It will do two things: keep the GPUs. So let me write this down in another color. The goals are, it will try to fulfill these goals. Keep the GPUs optimally busy, right? And the second goal that it fulfills is try to load local data into a GPU, because that can be pretty fast, isn't it? You can do shared memory access, and like you can just map, have the GPU, especially in architectures. And this, by the way, is now you would realize that this takes on new meaning because people are coming up with unified architectures in which the GPU memory and the main memory are either very close to each other or they are shared, right? So if they are shared, then you don't do any copying and so forth. So those are important goals for a distributed compute environment to fulfill. And when you do that, the experimental results are phenomenal. Actually, when you look at how well it does in benchmark, when you see how the GPUs stay busy, it does an incredibly good job. Right? Keeps it almost perfectly humming along. The other thing is that it keeps the GPUs, like if you know what the constraints of each GPU are, how much memory it has, and so forth, it does respect that. It doesn't try to shove more than the GPU can take. Right? So it will keep the GPUs optimally busy. It won't overload it. It won't underutilize it. And I can't think of too many frameworks that can, in a distributed environment, do such a good job of passing it through. So where is it relevant? Let's think through what are the situations where we can use something like this. We can use something like this, for example, in training of the model. right? You're training a model, lots of data needs to go through, it will do that. One other benefit it does is that, and it's the little things that makes a difference. For example, it gives you, like, for example, if you're training it, you realize that you would want the GPUs to take local computations in a way and do it on the local data. But in the next epoch, you want to shuffle the data, isn't it? So you realize that if you do a global shuffle, like if you try to shuffle the data across the whole data set, it will be expensive because now data has to move from one node to another, isn't it? So on the other hand, this framework actually gives you such niceties as local shuffle. I can say there will be a much more performant version. If you just shuffle the data locally, all of this data, if you can just shuffle it locally for the next epoch, that's good enough. Are you making sense? And so you could do local shuffling of the data, and then the next iteration of the training can continue, which is a huge, huge benefit. Right? The other aspects, so and these things actually, when you do the labs, you'll see these things make realistic, real world difference actually in the time it takes to train the models. Likewise, the other thing it does is it is very resilient to failure. If nodes go down, obviously in a distributed compute, it's one of the topics we talked about last time. Nodes will go down. Bad things will happen, and this framework is quite resilient to it. I mean, it better be. That's what distributed compute frameworks are. They're highly resilient to failure because they anticipate that failure is the norm, not an exception, right? So they keep recovering from that. The other thing they do very well is that they deal with heterogeneous compute. Heterogeneous compute. What does that mean? It means that suppose one node has a GPU and a CPU, but another node has no GPU, but only CPU, right? And as it is bringing in data, pushing things through, and this is the nice thing, the machine won't just ignore a node without GPU. The framework, the Ray framework, what it will do is it will say, you know what, let us do some computes on the CPU itself, right? So you could actually you could keep all the GPUs and CPUs fully engaged. And so the fact that it can do heterogeneous compute is actually one of the key strengths that this framework brings. You can, obviously you can say, well, GPU is going to be orders of magnitude faster than the CPU. Nevertheless, if you have a huge bank of CPUs available, why let it go to waste? You might as well use it, right? So those are the key things that you do get. And so let me recap what I just said. I said that this framework is very reminiscent, Ray data framework. It should be quite reminiscent of Spark, the mainstream distributed data engineering pipeline or framework, created by pretty much hugely overlapping teams. And it's quite mature. Actually, its performance is quite good, very, very good, actually. So at this moment, in terms of data loaders or data movement, I would say that Ray framework gives you close to state of the art. I mean, I don't know of anything that consistently beats the Ray framework. It's still at this moment at the leading edge. Right? If there is something, do please enlighten me. I may not be up to the latest, but to my knowledge, the Ray framework happens to be the state of the art. It's also very proven. It's created by a team that created Spark that has been for 15 years or 20 years, deep experience in distributed compute. So it isn't that these people are creating it for the very first time. These are people who are building it up after a decade or two of very, very in-depth enterprise grade data compute experience. Right? So Ray has to be taken seriously. As you will see, going forward, so we are doing a layered approach. We talked about the Ray core, which had only some basic primitives, task, actor, future, isn't it? and so on and so forth, and a distributed memory, global distributed memory, and so on and so forth. But under the covers, as you can imagine, and if you remember your Spark and other things, it is a beast. You have workers, you have executors, and so on. All of those things are still there, the drivers, etc. But it's a newer architecture. It has been conceived much more recently. And so it benefits from the hardware profile that exists today, and also benefits from the kind of awareness of the workloads that we are dealing with today. I would say, though, that if you are dealing with, let's say, just pure data engineering, one question that can come is it time to now move from, let's say, Spark or something to pure Ray? I would generally not advise that, partly because Ray API at the moment is evolving. It is not as completely written in stone as Spark is. Spark has a much longer maturity curve. But more importantly, in Spark, you can do, so let me just do this as Spark versus Ray. Spark you can do with SQL. And most people, it turns out that the majority of people doing data engineering, they treat Spark as something that lifts the whole data and creates an in-memory database, effectively, on which they can run SQL to do all the data transformations, right? And that is a reality today. 90% of the, I don't know the exact numbers, but if I had to guesstimate, 90 to 95% of the workloads in Spark are actually directly done in SQL, Spark SQL, right? At this moment, there is no equivalent. There is no Ray SQL. So just like with Spark or just like with Hadoop, at this moment, the inner core is a functional programming metaphor, like map, flat map, a batch, acting on batches, acting on elements, and so on and so forth. Like there, it used to be map partition. Here it is map batches in Spark. What was like that? So Ray, nevertheless, if you do want to play with Ray and treat it, like if you're doing AI, then I would strongly suggest that you use Ray so that you stay within one consistent paradigm. You don't keep switching back and forth, right? And Ray data is very mature. The only thing is you can't use SQL with it yet, right? And I'm pretty sure that as of today, you still can't use SQL with it. Right. So that is it. But as you use Ray, you will realize that it's a very simple, like I hope you must have realized last time in the homework that Ray core was quite simple. In a very similar way, Ray data is also very simple, but nevertheless, very high performance. Internally, the Ray data, so you may wonder, Ray data, how does it store the data internally? It turns out that it stores the data in the Apache Arrow format. Many of you know, Arrow has emerged recently as the darling of the data world, right? Especially the data scientist world, as the format to be chosen. And Ray data stores data or represents data as Arrow. Right? Now, Arrow, of course, coexists extremely well with all the leading Parquet and CSV and Pandas, let's say, right? Very good interoperability, PyTorch, and very good operability with leading compute frameworks like PyTorch, Hugging Face, etc. Are we together? One thing that I liked about Ray very much is that, we often do experiments in pandas, right? In a small data sets that we load in pandas. And the lovely thing about this is that a Ray data loader has literally a first class and trivial bridge to pandas. In fact, I would argue so far as to say that in some sense, it is easier to use, right? Many of the operations you can do very, very powerfully using Ray data, the data loader and Ray data, right? And it's really a pleasure to use, actually. That's what I would say. So that's a brief summary overview of this. What I would like to do is, after this sort of an intuitive picture of what Ray data is. Any questions before I start getting into the details? Anyone? What I would like to do is just walk you through the data. And I would also like you to watch a video, which I'll bring up in a little bit. And I think that says quite a bit by one of the core committers to Ray, and now I think a faculty at University of Washington. So Ray.io. Here we go. So if you go to the Ray data libraries, I will walk through it slowly. So what is Ray data? Why choose Ray data? It's faster and cheaper for deep learning applications. It certainly is fast. It's a very good, distributed compute framework. See, guys, a lot of people have created inference frameworks, right? A lot of people, like, they're inference-only frameworks. There are quite a few mushrooming all the time. Let's say that we are talking about VLLM and so on and so forth, SGLang and so forth. But the good thing with this is, Ray, first thing, it interoperates very well with them. It gives you inference of its own, but you can also interoperate, for example, with VLLM and so on and so forth. The other thing is that because it does data movement so efficiently, the distributed compute mode, it is actually very efficient and cheap. Cloud frameworks and data frame agnostic. I mean, it doesn't care. It works very well with everything, PyTorch, Hugging Faces, etc. So in other words, it's a Switzerland. I don't think that that is necessarily the biggest selling point, but it's a good point that it does interoperate as an open source project. And it does deal with the heterogeneous. I mentioned, we talked about that you can have machines with CPU, without, with GPU, without GPU, different powers of generations of hardware, and so on and so forth. And this has been the strength of Spark, and it is the strength of this also. More importantly, the dataset API gives you seamless integration with batch inference. So you realize that when you send data into, and especially into GPU, what do you send? You send a mini batch, right? Because that's the nature of it. It can take a mini batch of data. It's a tensor. And it actually does the translation from Ray dataset into that format very, very efficiently. More importantly, that is the online batch. There is the offline batch inference. Suppose you have a model. You say, hey, here is the data, and as part of the transformation, let us say you have lots of text. Let's take the most trivial example, lots of text. And for each text, you want to do sentiment analysis, right? You can just do batch inferencing. Batches of data go through that, and it will do that for you using the model and put it all through. So you can compare. Now, here are some comparisons, but I'll skip it. And people have done case studies with Ray data. For example, ByteDance has done. At the end of it, you'll realize, and these case studies, so may I recommend that you folks study these case studies, right? Because these case studies actually, everything that we just talked about, it will verify you. It will just make it more concrete when you see some real companies' problems and what they are dealing with. And so in this particular case, it's a Ray comparison to Spark, just to say how well they did it. So let's read the conclusion. In conclusion, with large models and keep looking ahead, we continue. Overview of how we leverage Ray Cube, etc. So anyway, it's a case study of how they did it. Let's look at the other one. Spotify, which most of us listen to, right? So again, they are using it. So needless to say, we are talking about major companies that are using it. A lot of big companies are using it in production, right? So do please take time out to read these case studies, right? Now, you can do comparisons to others, but I would rather that we not do it here. The quick start is, of course, our team. Chandra will shortly take you through a whole process. But importantly, I wanted to go over this. See, if you want to read data, I hope you see that this almost feels as simple as reading using Pandas API. If it was not Ray but Pandas PD, would you not just say pd.read Parquet or read CSV or read, let's say, read CSV? Right? So they have taken pains to align their API to something most of us are quite familiar with. Right? If you remember, this is the exact signature that you would use in Pandas. Right? The non-distributed version of it. And it's really very good. Likewise for text, read text. It will do that. It will give you row by row the text. And it can easily do the same thing, for example, with Google. If you have a GCS, right? There it is. It is reading. You can just give it a file system and some project, some file system, and do that. It can read from local just as well, from an NFS and so forth. And one of the lovely things which people used to appreciate about Spark was that if you have data compressed, which is the truth, if you have especially textual data, admits a massive compression. Typically, text if you compress, you can almost reduce the size by 95%. So good thing is that just like Spark used to do, or Spark does even today, this Ray, you don't need to uncompress the data. It will automatically do the optimal uncompression and use. Right? And you just have to tell it the format of uncompression. Right? You can load data easily. So Python, if you have a dictionary, like look at this, you're giving it some key value, like little maps, right? And it can load the data from maps, local maps. You can materialize it. Then you can read it from these items. You can load data, but not just from this local, but let's look at NumPy. If you have a NumPy array, it can read from NumPy. It can read from Pandas. And this part, by the way, it needs emphasizing. The fact that you can so easily interoperate with Pandas is lovely. In fact, I feel that they have made a conscious effort to make the API look so much like Pandas that the learning curve is very, very, like it's a very smooth learning curve. In no time, you're fluent with Ray data. Then you have, of course, if you do PyArrow, the arrow format, then of course it goes without saying that interoperates, because of course internally it uses arrow as its data representation. Right? Now comes the inspection of the data. Now, if you try to load data, that is all right from single block. What if you're using Spark? Then what can you do? Well, it interoperates with Spark. You see, data from Spark. If you have a data frame in Spark, you can just convert it to Ray. Right? And you can, in fact, Dask and other libraries are coming up, but I suppose at this particular moment, by far the most dominant library is still Spark. So I would strongly recommend that play around with it, since most of you do know Spark. Most of you come from the bootcamp 1. So you are familiar with the Spark framework. So do play around with it. But more than that, loading data from ML libraries. So if you remember, PyTorch, etc., they all have their data set. Like, for example, PyTorch gives you a datasets interface. They have their own data loader, which is called the data, and then loads it into something called a dataset, which is their notion of a large representation of data. Now, PyTorch dataset is a pretty good thing, but in my view, it does not have the same level of maturity or industrial robustness at scale, at massive scale, that you can achieve with PyTorch, especially in a completely distributed computer. But I must also say PyTorch is now doing an admirable job. It has more or less caught up or is catching up. Likewise, Hugging Face. Hugging Face at this moment supports parallelization only in certain circumstances. right? But they all are in different states of maturity, but Ray in this thing shines. Now, interestingly, you can do the same thing for databases. When you do it for databases, there are certain databases that are inherently, internally, massively big data computes or distributed computes. Like, for example, BigQuery, right? Or Databricks or Snowflake. And these things, obviously, very easily you can read from local nodes there. It's a very good integration. But even if it is not, actually, if you go to ordinary traditional relational databases, you'll notice that this framework tries to do a lot of parallel reads. It will sort of take the data and different ranges of the rows. It will try to do parallel reads if possible. Mongo, etc., etc. It also, of course, helps you create some basic data generation, but we'll skip that part. Right? Transformation of inspecting the data is a no-brainer. What can you do? If you want to inspect the data, look at it. It just looks and feels like pandas, right? If you look at this, guys, does it not look like if you have a data frame.info in pandas, that's how it looks like, the same call, right? In the same way, even the read function looks the same. If you ask it to tell its schema and ask it to print details, it will tell you so many rows, this is the data type, and so on and so forth. You can also do take all a data set, and it will take pretty much is the same as the head command in pandas. Pandas data frame head, right? Here becomes take. You can inspect it in batches. So you can say, give me a subset of data, a batch size of 2, right? Take batch. So it will give you not one row, but multiple rows. You could obviously look at various execution stats, but we'll skip that. Now, if you go to transform, again, you can transform at the level of rows. You can transform at the level of batches. So let's look at it. Row transform. Do you notice that the method itself is called map? If you're familiar with map, flat map, etc., from Spark, this should look, or from functional programming, from Java functional programming or Scala functional programming, or any of these, they should all look very, very familiar with it. And so what does it do? A map function takes a function that inspects a row of data and produces something new, a new row of data, isn't it? So this is it. In this particular case, it creates a new column called file name based on something, right? Base name. It just canonizes it. So that is that. And when you call this, you will get a data set, which is now, once again, the same lazy execution and all of those benefits that you expect in distributed compute, they all apply here. Transforming rows with flat map. Flat map is what? If a function takes one row or one item, but out of that produces a list of items, right? So then what it will do is you will end up with a list of lists now, right? And flat map just flattens the list of lists to a single list. That's what it is. So for example, if you take a row and just duplicate it, one row goes in, 2 rows come out, the second row being just a copy of the first row. This is a little cryptic, but that's what it does. And this is a very Pythonic notation. If you take a normal row and you multiply it by 2, you'll actually get 2 copies of the row. Right? So that's that. And when you print it out, you notice that it has duplicated the row. Flat map does that. Right. So likewise, you could act in batches. You could take a batch, and on the whole batch, you could do the operation. For those of you who are doing Spark, it is not exactly, but somewhat reminiscent of a map partition. Right? And you can configure your batch in NumPy, what's your batch, etc. What you could do it in pandas, right? Like with pandas, I find it so one thing that I may advise while you're learning it, and if you're very familiar with pandas, look at the way it interoperates and works with pandas data frame, right? Because it does, look at it. You can take batch from pandas. Like each batch, it treats as a pandas data frame of its own, right? And it works very well, actually. And how do you iterate? And now one part that is there. Remember, what is the core loop of a machine learning training? At core, a machine learning training happens as this. Just to remind you, for model training is this. For epoch, in a certain number of epochs that you have decided on, right? And here is the thing, for a batch in data set, and here is your inner loop, training step, right? You take one step of training on the mini batch of data. Do you remember that? You do the forward pass of the data, forward pass to get y hat. You compute loss comparing it y hat, right? Then you compute use the optimizer to do gradients. Optimizer and backprop. And then you finally do the gradient descent step. Well, you use the optimizer to do the gradient descent step. First, you backprop the gradients. Actually, I should do it. Gradients using just gradients and backprop and with. And then gradient, you use the optimizer to update weights with your optimizer, right, etc. So this is your inner loop. We won't go into the inner loop, but forget about this inner part. The most important thing is you need to pick up little batches of data. It's like taking a shovel of sand from a pile, from a large pile of sand. And so anything that is machine learning friendly has to give you a very sort of a good interface to that. And if you look at it, and as you will see, it does a very, very good job. By the way, the other transformers are group by, etc., map groups and so forth. I will skip that. But if you look at the iteration over data, it's just, especially over the batch of data. For batch and data, iter batches. Yeah. Yeah, please, if you could.
So this is kind of harder than known, but using the accuracy rate.
A little closer, I can't hear you.
Like using the accuracies that are in the report,
yeah,
right? Like this agents themselves as a distributed.
You mean agents as in AI agents, right? That's a good question. See, as far as the agents exist at the level of LLMs and executors, actors and agents are like, let's just say that those concepts live in different worlds. Actor is a very low level concept. It's a class that has been boosted to do remote computes. Agent is at a different level of abstraction. But I suppose, yeah, it's not easy to map one to the other. But the only thing suffices to say that if you do have agents, lots of them, the distributed compute framework will automatically make sure that if lots of agents have to work in parallel, a Ray framework will make sure that they are all scattered all over the place doing their work in parallel. That one is not, you're not doing it sequentially. That's what it will give you. So if you, now one of the lovely thing, and this was the local shuffle that I was talking about, that when you're doing computes, you're taking batches in training. Sometimes you want to shuffle it, right? So, and the training part is very, very straightforward. Look at this training for batch in this. By the way, if you're doing specifically PyTorch code, so you would say iter PyTorch batches, iter torch batches, right? You would just suffix a word or sort of interject the word torch because it becomes very aware of the PyTorch thing. So notice this. If we look at this code carefully, each worker is working on the local the data that it has been given, isn't it? right? And so you get local computes and a form of compute sharding. So that is it. Shuffling the data, as I said, the two local shuffles are better because they're compute efficient. Data doesn't move across the network. And of course, if needed, you could shuffle everything, random shuffle. But remember, random shuffle, one may be tempted to say, oh, of course, I have to random shuffle. But you need to be aware that random shuffle can be prohibitively expensive. Yeah. And so, many people feel that at every epoch you need to do global shuffle. Actually, that's not really true. But sometimes it is a good idea. You can do that, or you need not do that. Likewise, saving the data is a no-brainer. If you are familiar with pandas, can anybody see the difference between this and the pandas API? It's literally the same, isn't it? It's literally the same. Right. Writing to cloud storage, etc. Right? Let's see how it writes to Google. Again, literally the same. Like very, very, actually, no. I mean, I don't know if pandas can so efficiently write to GCS, but this can. Ray does it. Ray has native support for GCS and Amazon S3. And what is ABC? Oh, Azure Blob Storage. Yeah, I don't have experience with that. Writing data to NFS, network file system, again. And you can do, like, these are all things that have obviously been existing for a long time. I will, at this particular moment, say that you could look, the API is again very well documented, but I will in particular look at the torch, how well it integrates with the Ray data API, with the torch, read, parquet, bulk, etc., CSV, text, then binary. Pandas, of course, we already saw. NumPy we saw. Arrow is easy. In a moment, we'll come down to torch. Oh, by the way, Databricks, of course, Databricks tables. Read, does, Spark, easy, Mars, easy. And torch is as simple as this, one liner from torch, right? Literally from torch, right? So that is a small introduction. Now, may I suggest, after this, Chanda is going to give a lab example and walk you through the code. But before he does that, I would like to point out that in terms of resources, there is a YouTube for any scale. And in particular, I want you to watch one short video before the break. And after that, you can do a break. You can go on a break. It is this one, any scale. I thought this summarizes the key benefits of, let me go to this. Yes, so there is this video. Let me put this video. Okay, let me share. Share, copy. Should I put it on the chat? I'll put it on both.
Probably Discord chat.
Discord chat would be better, right? I do feel so. Let me go to Discord chat. It's a short video. I would strongly recommend that you go through that. Where is this corresponding? Not a bit from it. And MLOps. I'll just put it in the general discussion for now. Here's this video, guys. I'm going to stop the recording, and please take some time to watch the whole video before you go for